How's it going, everybody? Here to talk about TensorFlow and JavaScript today. My name's Nick, and this is my colleague Ping. And we work on TensorFlow.js here at Mountain View. So the traditional thinking is machine learning only happens in Python, right? That's kind of what everybody thinks about. But is that always the case? Has anybody seen this before? This is something we host on our TensorFlow documentation. This is the machine learning playground, the TensorFlow playground. And it was actually built by our colleagues in the East Coast. And it was just a visual to put into some of our ML classes. And it kind of shows how data flows throughout a connected neural network with different activation functions. And this was a really popular project we built. And it was a lot of fun to make, and we've gained a lot of traction from it. So we started to think, maybe it makes sense to do ML in the browser. There's a lot of opportunities for doing ML directly in the browser. We don't need any drivers. There's no CUDA installation or anything. You could just run your code. The browser has a lot of interactive features, especially with over the last several years of development. There's access to things like sensors and cameras. You can easily hook up to that type of data stream. And the other great part about doing ML directly in the browser is it's a good privacy use case. You don't have to send any user-facing data or any user data over the wire over an RPC to do inference behind the scene in your infrastructure. You could actually just do that directly on the client. So coming back to the TensorFlow Playground, this is about 400 lines of JavaScript code, and it was very specifically typed for this project. So our team kind of took this prototype and started to build a linear algebra library for the browser. This project was initially started, it was all open source under, it was called DeepLearn.js. And we took DeepLearn.js and aligned it with what we're doing with TensorFlow internally, with eager execution and that type of alignment, and launched TensorFlow.js last April already. And once we launched it, we had a lot of really great community and Google-built products, and I want to highlight a couple. This is one that we built at Google. It's called the Teachable Machine. This is all done in the browser. There's like 3 labels you can give what you're training in the webcam. There's like a green, purple, and red. And it sort of highlights how a basic image recognition model can run directly in the browser. So this stuff all exists online. You can still find it. Another community built a self-driving car all in the browser called Metacar. And this is cool. You can watch it train and learn the inference on what the car is driving. People built games. So this is a web game that somebody trained with TensorFlow.js to avoid. It's kind of a funny animation, but there's a little dude running back and forth, and he's hiding from those big balls. And the model is learning to avoid the balls all through using TensorFlow.js and continuing to play. This one's really cool. This is a Google project called Magenta, which does a lot of ML with audio. We have a large library called Magenta.js, which is built on TensorFlow.js to do in-browser audio. This is a cool demo somebody built. It's a digital synthesizer that learns how to play music and can drive with it. Another cool example that just came out is this is all community built open source. It's called Face API.js. So it's a library that sits on top of TensorFlow.js, has a few different types of image recognition, and can detect faces and facial features. So even like toddlers work pretty well. So I want to kind of showcase how our library pieces together. There's sort of 2 main components to TensorFlow.js. There's a core API and then a layers API. And that is all powered in the browser by WebGL. That's how we did the linear algebra aspect for the browsers. We bootstrap all the linear algebra all through WebGL textures. And on the server side, we actually ship our C code that we run Python. Or I'm sorry, that powers TensorFlow Python. So you get the high-end CPU, GPU, and then eventually we're working on the TPU integration story for server-side. And those who have used Keras, the layers API is almost the same as Keras, very similar syntax. The core API is our ops level, and anyone who's worked with TensorFlow save models that API will be pretty similar. Okay, what can you do today with TensorFlow.js? Well, you can actually just author small models directly in the browser. There's a limited amount of resources that browsers have, so we kind of get into that a little bit later. But right now, you can do pure model training in the browser. You can import pre-trained models. So this is a model that's been trained somewhere else, usually in the cloud or on some Python device. And we have a tool to serialize the model and then run that inference in Node or on the browser. And we have the ability to retrain models, so very basic transfer learning. We can bring in a model. Anyone who's seen TensorFlow for Poets, it's a very similar exercise. So to get started with the core API, I want to do just a very simple, basic fitting a polynomial. So this is a scatter of some data we have, and we're going to write a really simple model to try to find the best fit for that this plotted data. It's the classic fx equals ax squared plus bx plus c. Excuse me. So the first line, this is all ES6 style JavaScript for those who are familiar. So we're going to import at TensorFlow/tf.js is the name of our package, and we namespace it as tf. Now our first step is to include 3 different variables, a, b, and c, and we actually initialize those as 0.1. This is going to be passed into our training sequence. The next step to do is declare our function. So this is all using the tf.js APIs for doing that f of x equals ax squared plus b to the power of x plus c. And we have some sugar to make that a little bit more readable using chainable APIs, which is a very common pattern in JavaScript. Next step is to declare a loss function. Just have a mean squared loss. And then we declare the SGD optimizer with a default learning rate we've declared somewhere in this code. And then finally, we loop it through our training. So epochs, we pass through, and every step, we minimize our loss through the SGD optimizer. This is very similar to eager-style Python, for those who have done that in the Python land. Next thing I want to highlight is the next step up, that layers, that Keras-style API. And to do so, we've been working on doing audio recognition directly in the browser. And I want to highlight just simply how that kind of works. So really simple spoken commands like up, down, left, right can be run through FFT to build a spectrogram. So we take audio in, and we build a spectrogram as an image, and we train our model on that. And we can actually build that convolutional network pretty simply with our layers API. And the first step is just the same as our fitting polynomial. We'll include the package tf.js. And then we're going to build a sequential model. This is very Keras style, excuse me. Our first step is to do a com2d, a couple different filters and kernel size. ReLU activation functions. Again, this is very Keras, very familiar for those who've used Keras. Then we have a pooling layer. And then we're going to go ahead and do some more com2ds and another max pooling level. And so on. We repeat as we work our way down the funnel. And finally, we flatten out our layers, add some dropout, add a large dense layer at the very end, one more dropout layer, and then finally our softmax for audio labeling. And finally, let's compile the model. So this is, again, very similar to Keras. We're going to compile our model that we built. We'll know any errors that we have as the model is constructed, to give it an optimizer. And then we call model.fit to start passing in our training data with our labels. And once the model has trained, we can save it to disk. We have options for saving directly in the browser and on Node.js to file. And then finally, we can use that model to do prediction. So we model.predict, and we pass in our spectrogram. OK, so those were 2 quick passes at some of the APIs we use, the higher level core, and then the lower level, or I'm sorry, the higher level layers API and the lower level core API. But one of the cool parts of doing the browser is we can take in models that have already been trained today and build interactive demos. And for that, I want to showcase a small video. This is actually built by a collaboration of the TensorFlow.js team and a Google internal design firm. And we built this game for mobile devices. And it uses MobileNet to do emoji scavenger hunt. So on the game will suggest an emoji, and you have to run around the office and find it with your webcam on your phone. And this is all doing inference that's powered directly with the browser. For this one, I'll play a quick video, and it'll kind of give you a better highlight of what's going on.
This is an umbrella. So is this. This is a slice of pizza. So is this. Emojis have become a language of their own. We use them every day to communicate in our text and emails. So much so that it's easy to forget about the real-world objects they're based on. Which got us thinking, could we create a game that challenges people to find the real-world versions of the emojis we use every day? Introducing Emoji Scavenger Hunt. Emoji Scavenger Hunt uses TensorFlow.js. Open source meets machine learning meets JavaScript meets fun. It works like this. We show you an emoji. Use your phone's camera to find it before the clock runs out.
Hey, you found pen.
Find it in time, and you advance the next emoji. While you're searching, you'll hear our machine learning system doing its thing.
Do I see a toilet tissue? Was that a tub? Is that a glove? Hey, you found watch.
See if you can find all the emojis before the timer runs out.
Do I spy a broom?
Emoji Scavenger Hunt, powered by machine learning. Start your search at g.co/emoji scavenger hunt.
Do I see a URL?
Cool, so that sort of showcases where someone's already done the hard work of training a model, and now we can build that great interactive demo. Okay, so I want to highlight how we actually do that behind the scenes. So the first step is taking that pre-trained model. This is MobileNet. It's been trained under Python TensorFlow. Internally in MobileNet, those who have used MobileNet will know there's an object detector that you can tune for specific labeling. And then we import that into our JavaScript app, the scavenger hunt. First step, once the model's been trained, we save it. There's a few different paths for doing this. There's the traditional TensorFlow save model API. And then we also support Keras as well. So this is a sequential MobileNet model for Keras. Then we have a conversion step. So this is a tool that TensorFlow.js ships over Python. It's pip install TensorFlow.js, and you can use the TensorFlow.js_converter. For interacting with a save model, there's a couple different options for finding the output of the inference graph and where we want to serialize our artifacts. And then we also support the Keras style converter as well for HTF5 file format. And finally, we would like to load those artifacts into the browser. So this is all JavaScript code. For that saved model, it's tf.load saved model. And we have two different artifacts that our script creates. There's a weights link and then a link to the JSON file, which describes the inference graph. And again, there's the Keras style one. Keras actually ships all in one JSON file, which has one downside of it avoids some of the caching that we provide for save models. What happens in that model conversion step? So the first thing we do, especially like save model, has a lot of different paths for the graph. There's a inference graph, which is the one we want. There's steps for training, and a lot of time if you're using the TF data pipeline, there's actually graphs for all the data ops. So we actually pull out the graph for inference and then collapse ops as needed and run some optimization. And the one other great thing we do for a save model is sharding of weights into 4 megabyte chunks, which cache nicely with modern browsers. So it's only a one-time fetch for those larger models. And we support about 120 plus of today's TensorFlow ops in that conversion step, and we're always adding more. And again, the TF Keras layers are supported with this conversion step. I also wanted to showcase one more demo. This is a newer demo that we've just shipped this summer, and it's using PoseNet, which is a human estimation demo. And for this, I'm going to hand it over to Ping, who's going to highlight this.
All right, guys. So PoseNet is another example of converting a Python trained model and loading to the browser. So on the right side, you can see a lot of control that can fine-tune the model. And on the left side is a live feed of a video. So in the video, you can detect my face features as well as my body parts. And so this is a collaboration between Google research team as well as external contributor. So this model is in our model repository. You can check them out. On the left side, you can see actually has about 15 FPM, so frame per second. You can build some cool application like recognizing motions for sports, etc. We also have other models in that repository, so like audio command model that Nick mentioned earlier. And also we're adding some other like object detection model. So all of that is available for you to use in the browser. Just go ahead, check them out, and let us know if you build any cool apps. Thanks.
Yeah, the great part about that is it's feeding directly off of the camera feed in real time, and we're doing about 15 frames a second and presenting over the USB-C. So it does pretty well. OK, so I did mention earlier about training directly in the browser. This is the retraining, the transfer learning step. And for this, we have another cool demo that we want to showcase. Again, we're using MobileNet. And in this, Ping's going to pull this demo up while I'm talking. So we built this demo where we have a baseline MobileNet model that we've loaded in the browser. And we're going to train Ping's face to play Pac-Man. So he's going to start collecting samples from the webcam of what his up, down, left is. And so for this, he's going to use his face. So as he's moving his face around, he's collecting different samples that we're going to pass into that retraining step. So there's an up, down, left, and right. And then with this demo, as you hold down, we're collecting more and more frames. He's getting close, OK. And then now that he's collected his frames, he's going to click the train model button. And we'll watch our last shoot straight down. It only takes a couple seconds. And now he's ready to play Pac-Man. So go ahead and hit play there, Ping.
All right, let's go.
All right, this is a, there you go. So as the model is running directly in the browser, we retrained it to those pictures of his face. And the controls are lighting up left, down, right, based on what the model is doing. So, all right. So this is a great use case of what you could do with taking advantage of some of the stuff the browser provides and doing accessibility for machine learning and building cool apps. OK, Ping. We can play Pac-Man all day, man. These demos are all available on our site, which we'll showcase at the end. You can actually just run this today. No drivers, no anything to install. OK? Cool. All right, so I've shown off a bunch of demos of doing using our core API, using that layers API, bringing in pre-trained models and doing some basic retraining. So where does performance kind of stand for TensorFlow.js for our browser runtime, that WebGL-powered runtime? So this is some benchmarks we've done using Python and MobileNet. So there's two computers that we use for these benchmarks. The top one is a high-end workstation with a 1080 GTX, the high-end NVIDIA card. So it's super fast, a little under 3 milliseconds for inference time. And then we used a MacBook Pro, 13-inch MacBook with a non-integrated graphics card, or with a integrated graphics card, not a standalone graphics card. And that was using the CPU build, so it's just the default AVX instruction step we ship with TensorFlow. And we were doing a little under 60 milliseconds for inference time. So where does the TensorFlow.js benchmarks stand up? Well, it kind of depends. On that super beefy 1080 card, we were really close, about 11 milliseconds per inference time. The CPU, so running on this laptop, is a little bit slower. It's a little under 100 milliseconds per inference time, but that was still giving us that 15 to 20 frames per second, which allows you to still build interactive demos. So this discussion leads us to our next part, which is where does TensorFlow.js and server-side come into? We think there's a lot of great opportunities for going with JavaScript ML on the server side under Node.js. The ecosystem for Node packages is really awesome. There's tons of pre-built libraries off the shelf for NPM. You can build applications really quickly and distribute them on all these different cloud services. The default runtime for Node.js V8, super fast. It's had tons of resources put into it by companies like Google. And we've seen benchmarks where the JS interpreter in Node is 10 times faster than the Python. By enabling TensorFlow with Node.js, we actually get access to that high-end hardware, so those cloud TPUs, the GPU, and so on. So those are all exciting things. I wanted to showcase one real simple use case of Node.js and TensorFlow. The code snippet I have up here on the screen is actually a really simple Express app. If anyone's used it, it's just a request response handler. And we just handle the endpoint slash model, which has a request and a response that we'll write out to. So this model right now, actually, we have a model that we've defined, and we're going to do some prediction on input that's been passed into this endpoint. Now, to turn on TensorFlow.js with Node, it's one line of code. It's just importing the binding. So this is a binding we ship over NPM, and it gives you the high-end power of TensorFlow C library, all executed under the Node.js runtime. And what can you do today with server-side? So all those demos we showed of doing running the model in the browser, those actually just run under Node as well. You can use our conversion script. We ship the three major platforms, macOS, Linux, and Windows CPU. And then we also have GPU and CUDA for Linux and Windows. We just launched Windows late last week. And all the full library support, so the Layers API and our Core API all work today right out of the box with Node.js. And to kind of highlight how we can bring all these components of NPM and TensorFlow.js and Node.js together, we built a little interactive demo. So I know not everybody's super familiar with baseball, but Major League Baseball Advanced Media has this huge data set where they record using sensors at all the stadiums the different types of pitches that players throw at games. So there's pitches that are really fast that have a high velocity and low movement, and then there are pitches who are a little slower that have more movement. So we curated this data set and built a model all in TensorFlow.js that trains against this data and detects, I think, 7 or 8 different types of pitches and renders it through a socket. So don't get too hung up on the intricacies of baseball. This is just really solving a bread and butter ML problem of taking sensor data and drawing up a classification. So for this, I'll have Ping run through the demo.
Okay, so all right. So for web developers, you could really use TensorFlow.js to build a full stack kind of ML application. So on the left side is a browser that I started a client on the browser, inside the browser, which is trying to connect to the server through Socket.io. On the right side, I have my console. I'm going to start my server, Node.js server. Immediately, you see that it's binded to our TensorFlow CPU runtime. And as it goes, the model is getting trained. And the training stats are fed back to the client side. As the training progresses, you can see the accuracy increase for all labels. The curveball has about 90% accuracy right now. with kind of server-side implementation, it's easy to feed new data. Not like inside a browser, it's much harder. Let me try to click this button. What this would do is that we'll load live MLB pitch data into this application, and we will try to run inference on them. So let me click on that. So immediately you can see the orange bar is the prediction accuracy for all of these labels. Some of them we actually did better with the live data. It's 90% for change-up. Something we did a little bit less accurate. Fastball to seam is only 68%. So overall, I think it's to demonstrate that the model actually generalized pretty well for the live data as well. So yeah, back to you.
Cool. All right. I'm going to actually kill that demo or my laptop will die. Great. So just highlighting exactly what was going on there. There was the Node.js server, which was doing our training. There was a training data set and an eval data set, which we were reporting back over sock.io how good we are at each class through our evaluation. And then we had the ability to just easily reach out to MLB Advanced Media through Node and parse through their data and then send in that to the model, which was the orange prediction. So kind of a cool use case of I've trained my model, how does it stack up to real world data and doing like a quick visualization. And that was all plain JavaScript, plain HTML, and all the source code we've shown you today, all the examples we've shown you today are open source, and we'll link to them at the end here. So performance, so I highlighted where the WebGL runtime kind of stacked up with that Python benchmark. So let's step in and look at Python benchmark against the Node.js runtime. So again, these are those initial benchmarks I highlighted. The Node runtime itself is just as fast as the Python runtime for inference of MobileNet. This is because we're using the same library that Python uses, and there's not much code to get to, and then we're running on that high-end code. So, okay, I've highlighted a lot of stuff we've built since basically this year and launched in April. The Node stuff has been out since the end of May. So what's next? What's the direction that TensorFlow.js is looking to go in? We have some high-level bets that we're doing. There's a project that's going on that we're going to release here very soon in the next month or so. It's our visualization library. So it's the ability to pull in through the browser and do quick visualizations of your model and the data we have. So look for that coming soon. We also have a full data API, so very similar to the tf.data. It'll be browser and node specific, so there will be convenience functions for I just want to read data off of my webcam and not convert it to tensors. This API will provide that for you. And on the server side, it'll be giving highly optimized data pipelines for doing Node.js training. And so those are our two high-level things. Those are the big projects that kind of cross both of our runtimes. Looking forward for the browser, we're working on performance. So those benchmarks I showed with WebGL, a lot of them are, the bottlenecks are limitations for WebGL. So we use 2D textures to render the tensor data. There's some bottlenecks for downloading those textures, reusing those textures. So we're working on WebGL optimization. We're also adding more and more ops. Lately, the focus has been audio and text-based models, so we're adding a lot more ops to help with that. We have a great stable library of image recognition ops, and the audio stuff is coming. And the other thing we're looking at is helping push that spec. So the WebGL runtime was really interesting, and it kind of helped bootstrap ML in the browser. But WebGL isn't the best use case for this. And we're looking at a few different options. One is compute shaders, which is much more similar to a CUDA-like, where I can allocate the right amount of GPU memory I need to use and do that. And we're also following closely the web GPU spec. So there's a bunch of different offerings from Chrome and Internet Explorer and the browser vendors for what we want to do. We're sort of helping watch that space and provide guidance as needed. And on the Node.js side, cloud integration's a thing we're looking at. This includes the serverless type integration points, integration with our TPUs, and so on. We're actually working on generating opcode to provide all of the core TensorFlow ops in Node.js. The Python version of TensorFlow, most of the code is actually generated from our op registry internally. So we're writing that for TypeScript for JavaScript users too. And we're providing better async support with libuv. So libuv is the underpinning in Node.js for asynchronous programming. We're working better to make that scheduler work much nicer so we're not blocking as much main application threads. Okay, wrapping up. Showing you a lot of stuff. I kind of want to step back and highlight a couple things. First one's our core API. That's the bread and butter of the TensorFlow.js suite. It's our op library, allows you to interact with tensors. And we also have our layers API, which is our Keras style API for training. And we also support saved model and Keras model conversion today through our converter script. And the newest runtime we have is Node.js. We've just got done talking about a bunch of that. And with that, I want to thank you guys for attending. Everything I've shown you is on js.tensorflow.org. We have quite a bit of stuff up there. There's all those demos that I showed you. They're linked in that page, so you can find them as well as the source code. We also have a variety of GitHub repos. Everything we do is on GitHub. TensorFlow/TFJS is our root one. That's our union package. We keep track of all of our GitHub issues there. It also links out to a variety of things we have now. We have an examples repository, which has maybe 10 to 15 examples you can just run. There's also a link to our model zoo. So this is models that we've pre-trained, packaged up for JavaScript use, and published over NPM. A lot of them actually have wrapper APIs where you don't even have to take data and convert it to tensors and then pass it in for inference. It just says, here's an image HTML canvas. Can you do a prediction? So those are really cool. All that stuff's linked on TFJS. We also have a gallery, too, of community-built stuff, and it's always growing. This is our community mailing list. You can also find it on our website. There's a lot of good discussion for how do I do X, Y, and Z, or I need this feature. Can you please help? The gallery repo I just mentioned, that's where all of our community-built examples live. And models repo. And that's all.